kind of problem we have to do in dynamical systems. This problem is what happens to one swimmer. But we usually have to, when we look at turbulent states, we have to look at all the possible solutions of dynamics which are being explored by turbulence, and we have to figure out how to put them together. So this sort of self-centered image of the world works. So there's a great deal of literature, etc., how you do stuff in your own frame. We probably do it in quantum mechanics. We're not quite sure on nomenclature, but there are situations where this makes sense. I tell you and I describe in detail. I write some formulas, but this is the idea. So an experimentalist has a pipe, cares about turbulence in the pipe, and it's embarrassing because the thing is going 5 meters a second. So you either have to run by the side of the pipe and look at it or do something. But what you can do is now today you can take the data along the pipe and then you can bring it onto your table and say, oh, this state is like that state is like that. So that'll be the idea of why we will use this slicing. Now if you're a sophisticated kind of person, this might be called base manifold. So I'll explain. Slice is a local notion, just like Poincaré section. Poincaré section was designed to eliminate uninteresting motion along the trajectory and just focus on the transverse motions. Now you have more continuous symmetries. And they're quite different, so we give it a different name because calling them all Poincaré sections wouldn't do justice to Poincaré. He didn't do it. And they're different because we live in a Newtonian world where time is different from spatial transformations. General thing is that what this does is that you're living in some big world and you don't have to do this. So for example, the egoists don't do this. They don't actually go to one surface. They just do whatever they do without. A sensible choice would be to say, in this space, every point owns a group orbit. So these group orbits, they're all equivalent states. So one sensible thing to do would be to say, okay, I'll take a space, so this is dimension m, and if these are one-dimensional group orbits, I'll define some space which has dimension d minus 1, or in general d minus n for more parameters. If this manifold pierces every orbit I care about, then to every point in the big space, called xt, x at time tau, there will be a point g at time t which puts me into this submanifold. So that's the idea of the second thing. So you look at all occurrences or everything, just bring them onto your table, basically, where you've gotten rid of the translations. And anybody here is x hat. So x hat is in a small space and x is in a big space.